Welcome to Chemistry Lover, and in this video I will be talking about some of the very fundamental questions of inorganic chemistry which are related to bonding and molecular structure. So basically this discussion will be on the difference in the bonding of the different group elements, that is what is the difference with an element which belongs to same group but at a higher period, we can say. For example, in the first row and with the second row. For example, you can see the first question is, carbon dioxide, which is a gas, but when you consider the oxide of silicon, which is not actually the structure with SiO2, but we can say it the oxide of silicon, and they are basically solid. But you know that carbon and silicon, they belong to the same group of the periodic table, and we know that the molecules, or the atoms or the elements which belong to the same group of a periodic table, that shows the same chemical properties, right? But you can see there is a striking difference. One is gas, one is solid. Similarly, you can see silicon tetrachloride, it has a lower boiling and melting point than carbon tetrachloride, although if you consider the molecular weight, silicon has higher molecular weight, or silicon has higher molar mass than carbon. So you can expect that with increasing molecular weight, the boiling point and melting point should increase, right? But here you get the reverse result. And another question is, why ketone has structure like this? We all know that ketone has a structure like this, but the analogous compound silicon, when you consider the ketone analog of silicon, which is called silicon, that has a structure which has a very large polymeric structure, not a monomeric structure. So all these questions we will discuss. And another question is, if you consider the basicity between NMe3 and NSiH3 whole thrice, so this NSiH3 whole thrice, it is less basic than NMe3. So this is another question, and all these questions are related. So first we will start with this one, why NMe3 is more basic than this, and then the rest of the things we will discuss. So the answer to all this question is very simple. The extent of p-pi bonding, that is pi bonding between two pi orbitals of the adjacent atoms, versus the extent of p-pi d-pi bonding, that is one p orbital and the d orbital of another atom. So where the pi orbit, the p-pi bonding prevails, that give another result, and where the p-pi d-pi bonding dominates, there we get the other result. So for example, if we consider this NMe3 and NSiH3 whole thrice, so if we have to compare the basicity, we have to talk about the energy of this lone pair, the nitrogen lone pair. So higher energy the nitrogen lone pair has, higher it will be its basicity. Now if you just consider the inductive effect, what you can expect is this silicon compound should have more basicity, because silicon is more electron pushing or more electropositive than carbon, so it will push electron. So what I am trying to say is that, so if you have this SiH3 group, that will push more electron density towards this nitrogen, that and we would expect that the basicity of nitrogen should increase. Or if you consider the conjugate base also, you can say that due to this electron push, this nitrogen positive charge will be stabilized, whereas in case of NMe3, this same inductive effect is there, but the extent of inductive effect should be higher for silicon compound because it is more electropositive, but we are getting reverse result. Why? So yeah, this is right, this inductive effect thing, all argument is right, but we are forgetting a very basic point, that what are their structures. So this is another question, what are their structures? So if you consider this NMe3, that has a structure like this, where you have these methyl groups and this nitrogen is here, sp3 hybridized, and it has a pyramidal structure. The 3 sp3 lobes has this methyl group and one with this lone pair, so this lone pair is completely free to donate. Whereas if you consider the structure of NSiMe3, it will have a structure like this. Sorry, SiH3. So it will have a structure like this, where this nitrogen will be sp2 hybridized. Now, why this is so? So two reasons. One is because this carbon is smaller than silicon, so these methyl groups will have smaller size than this SiH3 group. So SiH3 groups are bulkier. Now the central atom is same and you are putting bulkier group. That means if you put bulky groups, they will tend to occupy more space in the more region in the space. And you know, in tetrahedral geometry, the angle between these bonds, this Me nitrogen bond, is only 109 degree, whereas in this trigonal planar form it is 120 degree. So of course the angle between these two bonds increases, and that's why their steric hindrance is lowered. So that's why, due to this bulkier structure of this silicon, it will prefer to adopt this trigonal planar geometry. Now the added advantage in this trigonal planar geometry is, you can see the silicon has vacant d orbital, right? Because it is a third row element, so it will have a vacant d orbital, and this nitrogen lone pair can be delocalized into this vacant d orbital, you can see. So this is one added advantage, and due to this delocalization, you can see this lone pair is not free now. So when you add some acid, this lone pair is not free, so they cannot react, they cannot capture that acid. So this is the reason why its basicity is lowered, right? So let us start from beginning. So the reason for the lower basicity is unavailability of the lone pair. Now why the lone pair is unavailable? Because it is delocalized into the d orbital. Now why it is delocalized into the d orbital? Because it has a planar structure, so that's why it has a chance for the delocalization. Now why it has a planar structure? Because of the steric hindrance. So the main point is the steric hindrance and the availability of the d orbital. And that's why these two show two different things. So the two questions which may come from here is, what are their structural difference and what are their basicity order, right? So that's all. Now let us try to answer this question, that why carbon dioxide is gaseous but SiO2 is solid. Now in carbon dioxide, you can see the structure of carbon dioxide is this linear structure, and there also exists a pi bonding like this, right? So there also exists a pi bonding, and this is one pi, this is another pi, and this is a p pi bonding. Now both carbon and oxygen, they are the first row elements, sorry, the second row element, and that's why they have the 2p orbital, and 2p orbital has relatively compact size, and their overlap is good. So this p pi bond is very strong, and that's why they prefer to aggregate within themselves to form this what we can say, this intramolecular structure, or we can say this monomeric structure. But if we imagine the same structure with SiO2, so if we can see this SiO2, so here the p orbital of this, here the p orbital of this silicon, this is the 3p orbital, whereas it is the 2p orbital. So first of all, because of the difference in the type of the orbital, one is 3p, one is 2p, so the overlap will be inherently weak. and also 3p orbitals are diffused inside, so they are very bad at forming any pi bond. So that's why these pi bonds would be very weak. And what will happen eventually is, so let's say initially they form this type of structure, but then when another molecule of this one they come, they will immediately attack over here, and by this attack gradually they will form a polymeric structure. Basically this is a three-dimensional structure of silicon, like what we can see in case of diamond. So in case of diamond all are carbon, but here if you replace the central carbon by silicon and then the other carbons by oxygen, you will get a structure of silicon oxide. So here at the added advantages in this polymeric structure, so you can see basically, so the structure will be like this: another silicon, another silicon, another silicon, and this is a never-ending big structure, big array. And here the added advantages, you can see this sigma bond, this oxygen silicon sigma bond, these are very strong. The added advantage is now the silicon also have a vacant d orbital, and this oxygen lone pair can stabilized or can come into resonance or come into conjugation with this d orbital also. So here you have very strong sigma bond, at the same time pi bond, the p pi d pi bonding is there. So this is basically p pi d pi. Now you can argue that p pi d pi bonding would be even weaker than p pi bonding. Yes, I agree with that, but it is an added advantage. The molecule is not forming this structure to get the p pi d pi bond, it is forming this structure to get this sigma bond, this oxygen silicon sigma bond. More number of sigma bonds is achieved. If you have only a monomeric structure, only 2 sigma bonds are there, but if you form this type of structure, you can see for each silicon there are 4. This is 1 2 3 4 sigma bonds. So number of bonds increases, number of oxygen silicon sigma bond increases, which is a very strong bond. So this is the driving force for this structure. Now after attaining this structure, it is added advantage that it has also this oxygen silicon p pi d pi bonding. So that's why it will adopt this kind of structure. Now the next question, silicon carbon tetrachloride. So carbon tetrachloride, we know that it has a van der Waals type interaction between 2 molecules. So this is a weak interaction, and that's why its molecular boiling point and melting point is lower. But why it is even lower for silicon and silicon tetrachloride? So in case of silicon tetrachloride, what happens is, so for silicon tetrachloride, again it has a d orbital and chlorine has a p orbital, right? 3p and here the 3d. So this p pi d pi bonding occurs, and there is a partial double bond character for each SiCl bond. And you know, if the double bond character arises, this bond length will be lower. So if you consider the molecular shape, molecular volume, so for SiCl3 and SiCl4 and CCl4, the CCl4 will have a bigger structure than SiCl4, because here you have carbon silicon carbon chlorine single bond. But in case of silicon tetrachloride, it is also single bond, but there is a partial double bond character due to this p pi d pi bonding, which is not possible for CCl4. Now both molecules aggregate themselves with the van der Waals force, and you know, if the size of the molecule increases, the van der Waals interaction increases. So that's why in case of CCl4 the van der Waals attractive force is more, and it has higher boiling and melting point. Now the last question is ketone and silicon. So again it is p pi versus d pi. So in case of ketone, this pi bond, this carbon oxygen pi bond, like the same way in case of carbon dioxide, this pi bond is a stronger. But for silicon, if you consider the similar structure, this pi bond would be very weak. So what will happen eventually is another silicon will attack here like this, and you will have a structure like this. Okay, so here is a positive charge and I mean negative charge, and again another molecule can attack, and that's why you will get a big chain structure, right? So this is the difference. So you can see all the difference is due to the size effect, the availability of the d orbital, the extent of the pi bond formation, these things. So I hope that you understood the concept. Thank you for watching.